Exercise 3.3.9, coordinate vectors for polynomials. Find the coordinate vector of this vector, x plus x to the fourth, and p sub 4. P sub 4 is the vector space of all polynomials of degree 4 or less, relative to the ordered basis of p sub 4 as given here. So we're trusting them that this really is a basis, a linearly independent spanning set. We want a coordinate vector. Well, it's fairly straightforward. If you know what the definition of a coordinate vector is, by the definition of coordinate vector with respect to an ordered basis, that is definition 3.8 in this section, we need coefficients. We need R1, R2, R3, R4, 1, 2, 3, 4, R5, such that, to find a coordinate vector is simply to find coefficients of these vectors in order, that's the ordered part of ordered basis, such that that linear combination produces the vector v. So we want linear combination, R1, coefficient, times first function, simply 1, the polynomial 1, plus R2 times second function, 2x minus 1, R3, third function, x cubed plus x to the fourth, R4, 2x cubed plus R5 times the last function, x squared plus 2, and we want that to equal x plus x to the fourth. So we've simply written an equation, a linear combination of the basis elements that produces this. If it really is a basis, there is a linear combination of these, it's a spanning set, that produces this particular vector. And we solve this system of equations, we create a system of equations and solve it. We find R1 through R sub 5. That is the coordinate vector of V with respect to ordered basis B. Okay, so let's take this, from it extract a system of equations. So as we've done several times, when dealing with polynomials, I want to collect together powers of x. So let's see, the highest power of x is x to the fourth. And we've got R3, x to the fourth on the left-hand side, and I think that's it. Whoops. R4, no, sorry, R3, x to the fourth. R3, x to the fourth. How about x cubes? Here's one, and here's one. So in terms of x cubes, we've got R3x cubed plus 2, R4 x cubed. Slightly tweak my style. How many x squares? Only one from the last expression. We've got R5 times x squared. X terms, here's an x term. Only x term is that one. So let's see. We've got 2R2 times x, constants. Here's a constant, here's a constant, and here's a constant. So in terms of constants, we have R1 times 1, R2 times negative R2, a negative R2 there, and a positive 2R5 here, plus 2R5. We want that to equal x plus x to the fourth. Maybe I rewrite that in a little more suggestive way. X to the fourth, 1x to the fourth plus 0x cubed plus 0x squared plus 1x plus 0. Now we match up powers of x. We're good to go. We got a system of equations. Okay, so left-hand side has our 3x4s, right-hand side has 1. This many x cubes must be 0 x cubes. Our 5x of 2 must be, our 5x squared must be 0 x squared, and so forth. So that allows us to produce the system of equations that we need. We need R3 to equal 1. We need R3 plus 2R4, the number of x cubes, to be 0. Next, R5, the number of x squares, we need to be 0. X terms 2r, x terms 1, we need 2r2, we need 2r2x to equal 1x, and the constant term on the left hand side is r1 minus r2 plus 2r5, and on the right hand side the constant term is 0. So we need to solve this system of equations for r1, r2, r3, r4, r5. Those are the components of the coordinate vector. So it's new verbiage, stuff about coordinate vectors and ordered bases. You play your cards right, it's the stuff you're familiar with. It's just a system of equations. So consider, let's turn that into a matrix. Try to squeeze it all in my little bit of space. Let's read off the first column. We've got we've got 0, 0, 0, 0, 1. Coefficients of R1. Coefficients of R2 are 0, 0, 0, 2, negative 1. Coefficients of R3 are 1, 1, and then zeros. Coefficients of R4, none others. Coefficients of R5 are 0, 0, 1, 0, and 2. We need that to give out the following. So there's the matrix associated with the system of equations. We'll ask Wolfram alpha to do its thing. It's a fairly sparse matrix because it has lots of zeros in it. But I know how to row reduce. We'll let Wolfram alpha take care of that. And Wolfram alpha will tell us, just happen to have it right here, that produces 0, 0, 0. First column, second column, or kind of as hoped. They're columns of the identity matrix. They're all columns of an identity matrix. They'd have to be. We knew those vectors were linearly independent because we knew we had a basis. Let's see, 1/2, 1/2, 1, negative 1/2, and 0. Okay, so Wolfram alpha gives us that row reduction. There's your R1 through R sub 5. There's your coordinate vector. So R1 equals 1/2, R2 equals 1/2, R3 equals 1, R4 equals negative 1/2, and R5 is 0. Hence, the coordinate vector, let's call it the desired coordinate vector, it is the coordinate vector, its full name is the coordinate vector of vector v, x plus x to the fourth, with respect to ordered basis b. The notation for that was we had the v vector with the ordered basis as a subscript, so we'd call it v sub b, and it's simply the R1 through R5 in vector form. So it would be R1, R2, R3, R4, R5. So that's why we did what we did. Find those coefficients. You do it using the powers of x. If you'll look at the numbers closely, it's no real surprise what's happened here. But what we've gotten out of this is 1/2, 1/2, R3 is 1, R4 is -1/2, and R5 is 0. So there's the coordinate vector of vector v with respect to this ordered basis. All coordinate vectors are coefficients in some linear combination. Linear combination involving the vectors in the ordered basis.